sound system design, sound reinforcement, and acoustics, okay? Yes, we're gonna cover all of that in one day, which means we're barely gonna scratch the surface here. So you should know that first, that this is, I mean, the sound reinforcement part is fine. We'll take some time on that. The acoustics part, we're gonna go real quick. We're gonna learn some real basic stuff. And, you know, there are people who dedicate their entire careers to acoustics. So, and we're going to talk about it for a day. So, you know, we're not going to get too into it, but we're going to cover a little bit. So let's take a look here. The first part is sound reinforcement. So what we mean by sound reinforcement is, this is what some people would call sound amplification. And sound professionals tend to not really like that term because we are, at least in live rooms, you will always have that natural sound. You can't truly amplify that natural sound. It is what it is, and you will hear it or not hear it regardless of whether we show up for work and turn on the sound system. So we prefer the term sound reinforcement because that's, you know, it better describes what we're trying to do. We're trying to take something that is already happening in the room, and we are trying to reinforce it with something else, right? Something else that's coming out of a loudspeaker or something. But there's no knob I can turn on the person and make them louder, right? I can only put a microphone on them, pick up the thing they're doing, and make that thing come out of a speaker. And that's, you know, I don't think the word amplification really is an accurate way to describe that. However, there's something that we need to understand about sound reinforcement, that of course we know that we call that there is a sound reinforcement system. And probably you're familiar with some parts of the sound reinforcement system. We've talked a lot about loudspeakers, right? We have talked a little bit about microphones. Those are two very important parts of a sound reinforcement system, but there are two other parts of a sound reinforcement system. And if you didn't have these two things, you know, the loudspeaker and the microphone wouldn't matter. And that is a talker and a listener. Okay, so the talker and the listener are part of your sound reinforcement system. The listener, of course, is the person who is going to hear all this stuff. If no one, you know, if a sound engineer turns on a sound system and no one's there to hear it, doesn't make a sound, you know, I don't know, but you certainly need someone to listen to it. And we tend to prefer the word talker rather than speaker for reasons that might become clear if you think about it for a second. Because we could use the term speaker and that could apply to two different parts of our sound system. So we tend to like to use the word loudspeaker and the word talker, or sometimes you could say singer or actor or something, but try to avoid the word speaker when describing the person standing on stage who is doing the talking or performing, because that can get confusing sometimes. So, so far, you've probably all had some experience with this kind of sound reinforcement system, where you have a talker and a listener and a microphone and a loudspeaker. And what happens is you turn that system on, and maybe you've got a little fader on the mixing console. The person starts talking into the microphone, and you push that fader up, and you're trying to get it as loud as you can get it because we get paid and gain. And eventually, what happens? Like you're gonna push that fader up, and something, you know, eventually you're going to have to stop pushing that fader up. Why? Anybody, any ideas why you would have to stop pushing that fader up?
Feedback.
Feedback, right? Yes. So eventually it feeds back. Feedback is the limiting factor. So we've talked a lot about so far in the class things like, you know, how loud you can get these things. You know, what is the sensitivity of loudspeaker? You know, how loud will it get if you put this many watts into it, and all the way at the back row and all that stuff. And all that's true. But the truth is you probably will never get to those maximum sound pressure level output because of feedback, right? Feedback will stop you before you get there. So what is happening with feedback? Well, feedback is actually a problem of geometry, okay? And I'll explain more about that later, but I want you to notice here that I've got some measurements of different distances here. So feedback is the result of these distances between these four components of our sound system, and whether those distances are appropriate or not appropriate for what we're trying to do. Let me see if this is going to work. I've got a little annotation thing here. Let's try it. So there's this distance, right? we're going to call that ds, and that is the distance between the talker and the microphone. Okay, and then there is d1. d1 is the distance between the microphone and the loudspeaker. And then we have d2. Let's see here. d2. And that is the distance between the loudspeaker and the listener. And then d0 is the distance between, it's already getting a little rough here. There we go, D0, you see it, is the distance between the talker and the listener. Okay, so those distances and their relationship to each other will decide how much gain you have before feedback. And by gain, I mean, how much louder are you able to get it? Okay, so let's take a look at what's going on there. Oops, turn that off. No, okay. All right, so, hang on. I didn't start the, I'll show you. I'll do that real quick. Okay, so here's what's going on. You have, this little symbol represents the microphone. This little symbol represents your fader in your mixing console. This symbol is the power amplifier, and this symbol is the loudspeaker, okay? So sound comes into the microphone. You decide how much you want to use the fader to let that audio pass through. That goes into a power amplifier, which then goes into a loudspeaker. That loudspeaker makes sound. Here's what happens, though. Some of that sound that comes out of the loudspeaker gets back into the microphone. And based on the distance between the loudspeaker and the microphone, there will be a certain frequency that, with that given distance, it will sum together with the other sound that's coming from the talker, and it will lock into some sort of 0-degree phase relationship. And that's what we're looking at here. So up here at the top is this is the sound of the talker, okay? And I'm just using pulses here to indicate those sounds. And then after a certain amount of time, the sound from the loudspeaker makes it back to the microphone. And based on the wavelengths and of the various frequencies and their connection with that particular distance or time, there will be a certain frequency that has traveled some certain multiple of wavelengths before it gets to the microphone and is arriving at the microphone at the same phase relationship as it's the copy of that frequency that's coming in from the talker. When that happens, well, what happens when you get two sounds, two frequencies that are the same, that arrive at the same time, at the same level, and are the same phase relationship? What happens to those two sounds when they come together?
They sum.
Yeah, they sum. They get louder, right? Like 6 dB louder. So now you've got this one frequency that suddenly gets 6 dB louder. And then that 6 dB louder frequency goes through the amplifier again, comes out of the loudspeaker, 6 dB louder than it was before, makes it back to the microphone where it sums together with a copy of itself again. You get another 6 dB. And it just keeps going. This is why feedback gets louder and louder and louder the longer you let it go. Because each trip it makes through that, what we call that electroacoustic path, it picks up 3 to 6 dB. Boom, 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 boom. And it just keeps getting louder and louder and louder until you do something. And usually what you have to do is adjust that fader level to reduce that 6 dB boost. So here is the very, very important take-home message. If you remember nothing else from our conversation about feedback, it should be this: that feedback happens when the sound from the loudspeaker arrives at the microphone at the same level as the sound from the talker. Okay, so when the sound from that loudspeaker travels through the air and gets to the microphone, and there's enough of it left after traveling at that distance that it is the same level as the sound from the talker. So those two things are arriving at the same level. That's when feedback happens. Because that's how a reinforcement happens, right? You get a perfect reinforcement when two sounds combine at the same level. So generally speaking, avoiding feedback is about trying to get the difference in level between the talker and the loudspeaker that's hitting the microphone. You want to get those as different as you possibly can in level, and then they won't do that 6 dB summation, and you won't get the feedback. Does that make sense? Any questions about that? Okay, so let's take a look at how this works. So we're going to do just a little bit of math here. So here I've got a sound system set up, and I'm going to give you some distances here for each of our little relationships. And we're going to do this in meters just for fun, because it'll make the numbers smaller in this particular case. And we like small numbers. So ds, which again is the distance between the talker and the microphone, is going to be 1 meter. d0, which is the distance between the talker and the listener, that's going to be 7 meters. d1, the distance between the loudspeaker and the microphone, is going to be 4 meters. And d2, which is the distance between the loudspeaker and the listener, is going to be 6 meters. So why do we care about that? What's important? Well, let's take this into practice. I said to you that feedback happens when the sound from the loudspeaker, the sound here, gets to the microphone and hits the microphone at the same level as the sound from the talker. When those two sounds hit the microphone at the same level, that's when feedback happens. So let's just see if we can work through this a little bit. Let's say that the talker is talking into that microphone and you get 70 dB at the microphone. 70 dB SPL is the level of the talker when it hits the microphone. So we know that feedback will happen when the sound from the loudspeaker also hits the microphone at 70 dB SPL, right? Because I just said that. And what we want to figure out is, if that is happening, if the loudspeaker is hitting the microphone at 70 dB SPL, how loud is it over here at the listener? How might we figure that out? Well, we could do a 20 times the log of d, well, the distances. So let's start by just doing the level of the talker if we don't show up for work, okay? So this would be 20 times the log of d0 divided by ds, okay? d0 being the distance between the talker and the listener, ds being talker to the microphone. So the difference between those two distances. So I would do d0 is 7 meters, and I will divide that by ds, which is 1 meter. We'll do log 10 times 20, and I get 16.9 dB. So we would then subtract that from the 70 dB that the talker was doing at the microphone. So 70 minus that number, and we end up with 53 dB SPL. So what that means is, if the talker is talking into the microphone and that level is 70 dB SPL, here at the listener is hearing 53 dB SPL because of that extra distance that sound has traveled. Okay, it will be quieter at the listener than it will be at the microphone because the listener is just farther away. So in this case, it's going to be 53 dB SPL. Did everybody follow that? Any questions about that? Okay, so remember that number, 53 dB SPL. Somebody write that down, because we're going to need it in just a second. Okay, so now what I want to know is, if the loudspeaker is hitting the microphone at 70 dB SPL, which is the loudest we'll ever be able to get, because once we get to that point, we're hitting feedback, okay? So if that's happening, how loud will the loudspeaker be at the listener? Okay, well, this will be, so we turn the sound system on, we run it all the way up to the edge of feedback. This would give us 70 minus 20 times the log of d2 divided by d1, the difference between those two distances. Okay, so d2 is 6 meters, so we're going to do 6 divided by d1, which is 4 meters, so 6 divided by 4, log 10 times 20, and we get 3.5. Okay. So now I'm going to take our 70 dB SPL that we know that's what it's doing when it hits the microphone, and we'll subtract that 3.5 dB, and we get 66.5 dB SPL. Okay. Now, what was that magic number that we looked at before? How loud was the talker at the listener without us showing up to work?
53.1. Okay.
So what I'm going to do is I'm going to subtract that from this number. So minus 53.1, we get 13 and some change dB of gain. Okay, so this is the maximum gain that we're able to get with this sound system. In other words, we show up for work, the talker does the talker's thing, the listener does the listener's thing, we turn on the sound system, and we can make this show 13 dB louder than it would be if we didn't show up for work. That's called gain. We gained 13 dB. We can't do any more than 13 dB because, you know, at 13 dB is when it starts feeding back. Okay? So it doesn't matter that the loudspeaker's got another 30 dB of headroom in it. We don't get to use it because it's feeding back. However, here's kind of the catch here. Well, actually, before I talk about the catch, let's just review what we just did. So if I were to string together into one long equation what we just did, it's this that's down at the bottom of the screen. We did 70 minus 20 times the log of D2 minus D1 minus 70 minus 20 times the log of D0 divided by DS. Right? That's what we did. That's the math we just did. If we string it all together. And we got out of that 13.5 dB of gain. However, you don't really want to be right at that feedback point because that's when it starts feeding back. And the system's going to be kind of ringy, right? You've probably been in that situation where you're right on the edge of feedback and it's not feeding back, but it's just ringing a little bit. It keeps trying to feed back, and you don't want to be there. That's what happens when you're at that 13.5 dB in this case. So usually we want to be 6 dB below that. Why 6 dB? Because 6 dB is that magic number that you get with the perfect summation. So you want to be away, at least 6 dB below that point where it starts ringing, so that you don't have any risk of any ringing that will happen. So here is another version of that equation with that 6 dB safety factor. I'm not going to get into the algebra of why this works, but this is basically what we did. Now here's what I want you to do is run this equation, this new equation, and tell me what you get. Because remember, we had 13.5 dB with this top version. Now, in reality, we would subtract 6 from that to have our safety factor. So if we were 13 dB minus 6, we'd really be more like 7.5 dB to be safe. So somebody run this equation, 20 times the log of, in parentheses, D1 divided by DS times D0 divided by D2. Each of you run that, and let's get some answers here. Tell me what you get.
I got 7.38.
Anybody else get that? That's what I got. So I need one more person before it'll be right.
7.38.
Yay. Okay. So aside from just, things being organized a little bit differently, what do you notice about this second version of this equation? What is not there that was there in the first part of the equation?
The 70.
Yeah, and what does the 70 represent?
The level that the talker is speaking into the microphone.
Right. So here's what we just proved, and this is going to blow your mind. We just proved mathematically that the level of the talker has nothing to do with your gain before feedback.
Mic drop.
Right? Because we can either consider that variable or not consider that variable, and we can get the same answer. Okay? It doesn't matter how loud they talk. Your gain is the same. How many times have you blamed a poor actor on your gain before feedback problems, and when in reality you just had a crappy sound system? Okay? Your gain is not their fault. Okay? Now here, so let's take a look at what we're talking about here. Well, I thought I had a slide for that, but I don't. So here's some observations. One is that, yeah, okay, gain is independent of the level of the talker. Doesn't matter how loud they talk, your gain will be the same. But let's sort of like take that apart a little bit, because what we mean is whatever they do, whether that's 50 dB SPL or 70 dB SPL or 90 dB SPL, you will never be able to do more than 7.5 dB more than that in this sound system, right? You can only make it 7.5 dB louder than what they're already doing. So even though the level of the talker has nothing to do with your gain, it is true that the louder they talk, the less gain you might need in order to get them, to be understood and heard by the audience. So that is true, but not always. I mean, if it's an enormous room, it may not matter how loud they talk. If you don't have enough gain, it's just, doesn't really matter. They could talk as loud as they possibly could, and if the back row is 300 feet away, and you don't have enough gain, that's your problem, not theirs. There's no amount of them talking louder that's going to fix that. So I want to show you a little demo here. So this is from, you like that? So this is from our book. And I've got a little flash demo we can play around with here. So, okay, here you go. Here's our sound system. We've got a microphone, a loudspeaker, a sound source, which in this case would be a talker, and a listener. Don't forget, we also have an operator over here. This is usually us, back in the corner with our little mixing console. Okay, here's those same distances. And here's the equation that we just talked about. Now, what I want to show you is, in this particular situation with these distances, we have a potential acoustical gain of 10 dB, okay? Now, what's cool about this little demo is the math is built into the computer code here. So we can actually drag these things around and see what it does to our gain. So for example, if I take my loudspeaker here and move it back here, what happens to my gain? Okay, it goes down. Why? Because the loudspeaker is getting closer to the microphone but farther away from the listener. Therefore, it's getting louder at the microphone and quieter at the listener. Okay, watch this. What if I take the loudspeaker and take it right up above the listener's head? Now I'm at 31 dB of gain, right? Why? Because the loudspeaker is really far away from the microphone, and therefore it's quieter because of inverse square law. And it's really, really close to the listener, and therefore we haven't had to give up so much by traveling through the air. Watch this, though. What if I take the talker and bring the talker closer to the mic? Okay, if I can get the talker really, really close to that microphone, I can get 39 dB of gain. And even if I bring the loudspeaker back here to that spot where it was before, where it's now behind the mic, and now it would be hitting the mic pretty loud, I still have 33 dB of gain. Why? Because whatever the talker is doing, we're not giving up any of that sound by traveling through the air, because the mic is right up against their mouth. So all of that work that they're doing, we're capturing all of it, which really helps with our gain. We're still getting 33 dB of gain, which is a lot. You'd get paid pretty well for that show. Okay, now, so if you can do this, and you can get the loudspeaker in a good spot, I can get 40 dB of gain here, which is even better. So let's sort of review those relationships. So here's a scenario where we have 1 dB of gain, right, which is basically nothing. Okay, we may as well have not set up this sound system. So we know that if we can get the loudspeaker farther away from the microphone, gain goes up. Now we're at 7 dB. If we can get the loudspeaker closer to the listener and farther away from the microphone, gain goes up. Now we're at 19.5 dB. If we can also get the talker as close to the microphone as possible, gain will also go up. Now we're up at 41 dB of gain. So I've managed to go from 1 dB of gain before feedback to 41 dB of gain before feedback, and I haven't yet touched an EQ. Anybody ever tried to use an EQ to fix your feedback problems? Yeah, okay. How much extra gain do you get by using the EQ? How much more level?
So little.
Yeah, maybe a few dB, right? Best case scenario, a few dB. Maybe 6 if you really use a ton of EQ filters, maybe 6 dB. But what happens to the sound after you've engaged all those filters and now you've got your 6 dB? What does it sound like?
Sounds funky.
Yeah, it does not sound right? Because you've just obliterated so much of the frequency spectrum in order to avoid your gain. So you could obliterate your frequency spectrum to get yourself 6 dB of gain, or you could just move things around a little bit and get yourself 41 dB of gain. Much better bang for your buck in that scenario. Highly, highly recommend that. The other thing is, this doesn't necessarily cost you anything to do this either. You don't have to buy any equipment. You don't have to, I mean, you might have to pay some labor to move the loudspeaker maybe, but this is a pretty cheap solution. You don't have to go buy anything. And, you know, producers tend to get really annoyed with you when you tell them they have to buy equipment to solve a problem, and then that problem doesn't get solved after they spend all that money. They're probably not going to listen to you the next time you tell them to buy something. So I would highly recommend that you try this kind of stuff first. So let's take a look at what we're talking about here. The other thing you can, other than an EQ, there are other ways to increase your gain other than moving stuff around. One is to use directivity to your advantage. So you could use a directional microphone. Up until now, we've been assuming that the microphone was omnidirectional. So if you notice here, we're in this scenario where we have 4 dB of 4.5 dB of gain. But what if I switch the polar pattern of the microphone? So right now it's omnidirectional. If I go to a cardioid, look at that, I get 16.5 dB of gain now. Why? Because this microphone is less sensitive to sound that comes at it from this back angle like that, okay? So even though the sound is hitting the microphone pretty loud, the microphone doesn't like listening to sound from that side, and therefore it doesn't pick it up as well. I can go to a hypercardioid, and I can get all the way up to 30 dB of gain. Why? Because there's got this, you know, that one has a little node that happens to line up right with my loudspeaker. I can make it even better if I just move this around a little bit. And again, you know, get the talker as close as you can. Now look at that, I'm up at 55 dB of gain, and the loudspeaker is only 9 feet away from the mic. See that? Isn't that cool? Now what if I take this up in the air? Now I'm at 60 dB of gain, right? Now I've really got something. So that's a scenario where you could spend a little money to get a different microphone and maybe get yourself some more gain. There's a problem with this strategy though. Can anyone guess what this problem would be, given what we've learned about directivity?
So that's only going to work for your higher frequencies.
Correct, yeah. So this microphone is directional, but it's probably only directional at higher frequencies and not really for lower frequencies. The lower frequencies are probably going to be more omnidirectional. So while it is true that using a directional microphone can get you more gain, it's probably not going to be an extra 23 dB of gain like is indicated here. We're assuming that this is a pretty high frequency. So some strategies for dealing with that is, you know, like when I'm doing a show, I will almost always put in low pass or high pass filters on all my mics that are live on the stage. So, you know, sometimes all the way up to 120, maybe 200 hertz, because for most voices, there's just not a lot of information going on down there. And that's where the microphone is omnidirectional anyway. And so I can sometimes get a bit more bang for my buck out of these directional microphones by filtering out those low frequencies, because I don't need them. I'm not trying to pick those up. So there's no point in trying to amplify them because all that's going to do is destroy my gain before feedback. So that's the one scenario where I think using an EQ could be helpful, is just using high pass filters on these microphones to filter out those omnidirectional frequencies. That way you can leverage this directivity as much as possible. Now there's another scenario where you could use directional loudspeakers, okay? So, you know, here I've got, we were assuming the loudspeaker was omnidirectional, but what if we can get a more directional one? So, you know, here with a 90-degree loudspeaker in this scenario, I am still using the hypercardioid microphone, but with a 90-degree loudspeaker, I'm able to get 52 dB of gain. Whereas, you know, if I went back to the omnidirectional microphone, I get an extra 22 dB of gain by having a directional loudspeaker as compared to omnidirectional. But what if I go to a much narrower pattern? What if I go to 40 degrees? Ooh, now I'm getting 28 dB of gain using this directional loudspeaker, right? I only get 26 dB of additional gain with the 60 degree, 22 or 23 with the 90. So this is where directivity can become your friend. So where we've been talking about directivity so far, we've been talking about, okay, how do you distribute the sound evenly across the audience? But the thing you've got to also be aware of is you've got to figure out how to get it to be even across the audience, but as little of it as possible to hit the stage. Because for every amount of sound that you can avoid hitting the stage, that's an amount of sound that doesn't get into the mics, and you don't have to worry about gain. Now, with a loudspeaker, you have all the same problems, right? About different frequencies have different directivity. So the low frequencies are going to be more omnidirectional than high frequencies. All the more reason to engage those high-pass filters. In theater, we tend to not be able to leverage directional microphones as much because, most often we're talking about, wireless lav mics that are on an actor's head. Those tend to be omnidirectional because we can't always get them in the perfect spot. The perfect spot would be right here in front of their mouth, right? And if we can get it right there in front of their mouth, then yeah, we could do a directional microphone and it would sound fine. But we tend to end up having to put it up here, or over here, or something. And if it was a directional mic, then we'd be off axis of it there, and the frequency response would be all wonky. So we tend to use omnidirectional mics so we can put them anywhere on their head and it sounds, more or less the same. So we tend to not be able to leverage the directional microphones, but directional loudspeakers, yeah, you better believe we can use that. Anything you can do to keep that sound from the loudspeaker from hitting the stage, then it won't hit the mics either and you'll be in good shape. But if we can also get that talker as close to that mic as possible, so get that lav mic as close to their mouth as we possibly can before the pretty committee cuts us off, then we get a lot more gain. So here I am with an omnidirectional microphone, a directional loudspeaker, and I'm at almost 63 dB of gain before feedback. All right. So let's take a look at what this means. So just in case you're not quite there, let's try this out. So here's a scenario where we have only 1 dB of acoustical gain. What does that look like to you as the operator? So here you are, you're on your fader, and you're pushing the fader up. And this blue range is the range where you haven't amplified it enough yet to even hear anything coming out of the loudspeaker. It's too quiet. Okay, the green area is where, okay, you're starting to hear something out of the loudspeaker. It's starting to make a difference. Okay, so you get a little, so you're pushing it up, nothing. I may as well not even turn this on. Nothing's happening. Okay, something's barely happening. Oh, and then it's automatically feeding back, right? Anybody been in that situation? Where it's like, okay, I'm doing nothing, barely something, feedback. Okay, that's not a good place to be. You're probably not going to get paid very much for that show. So now let's just do a simple thing of getting the talker closer to the microphone. Sometimes that's the easiest thing to do. Now what happens up at the mixing console? Hey, look at this. So you've got nothing, but then you've got all this green area, which is more. It's getting louder, and you can get it all the way up here before you hit feedback. That's a much better situation to be, right? You're going to get paid a lot more for that show. It's going to be a much easier tech week. I know you're going to have a lot less people shouting at you because you've got a whole lot of room here to play with your gain. You can actually be creative here, right? You can boost the level when it needs to be loud. You can duck it when it needs to be quiet. You've got room to work. All right. So that's what we're talking about here. So the things I want you to keep in mind here are this notion that, the talker and how loud they're talking doesn't have anything to do with the gain of your system, right? The amount that you're able to gain is a fixed level that has nothing to do with how loud they talk. You can only make it X number of dB louder than whatever they are already doing. Fixing that problem is more about fixing the geometry than fixing the frequency response. So you got to move things around to fix that problem, to get that gain before feedback to go up, okay? And then do everything you can to leverage directivity to your advantage. Try to leverage the directivity of the loudspeaker in such a way that keeps the sound off the stage. If you can use directional microphones, use them. But certainly do everything you can to get that microphone as close to that talker as you possibly can. That's going to get you the best result. All right, any questions about acoustical gain?
I have a question.
Yeah.
On the equation that you have on the slide that's up right now, the simplified one, why do we
Yeah.
subtract 6 at the end of it?
So that's to be that 6 dB below feedback. So if you don't
Got it.
have that,
Okay,
then
cool.
basically you are at feedback,
Perfect.
right? And you want to be 6 dB below that point where it starts feeding back. So we call that the safety factor.
Got it.
Another quick question on the slide previous to this, it said the range was PAG. What does that mean?
Oh, potential acoustical gain. So, you know, we use that term in the book just because, you know, as you will discover in real life, the math doesn't work out exactly the way you would think it does. The math will tell you the potential for what you're able to achieve gain or feedback wise, but there's other variables that we're not considering here, such as, you know, reflections, noise floor. There's other issues that would affect, you know, the way you perceive that gain. So even though you might have the potential of achieving 30 dB of acoustical gain, you may not really ever realize that fully because of some of these other factors. So it's just to remind you that that's the potential, not necessarily the reality.
Okay, this may be a bigger question, but
Yeah.
this summer I worked with a designer that had me take all of the mics and we walked around stage in a silent room, and he had the A1 crank it up until it had feedback, and then he was doing EQ changes.
Right.
Was that attempting to EQ out gain? Like,
Yeah.
do you know what he was doing?
Yeah,
I don't.
This is a process called ringing out the mic or ringing out the system. And the idea there is you're going to try to, and the reason you move around is that you're changing the distance, right? You're changing the distance between the loudspeaker and the mic. Different frequencies are going to lock into that feedback loop. So he's trying to find, you know, the frequencies that feed back and kill them in an EQ, right? So if you put an EQ into that signal path, and if you can kill that frequency that's trying to lock into a feedback loop, then it's basically getting muted while it's going through the sound system, so it doesn't feed back. This is actually a pretty common practice. The problem with it is that doing that screws up your frequency response, right? So you'll spend a whole lot of time tuning your sound system to get it to sound really great. You're going to do a really high quality omnidirectional microphone on that actor, so it sounds really great. You're going to EQ it so they sound awesome and everything's awesome. And then you're going to take a graphic EQ or something, and you're going to just start notching out feedback frequencies left and right. Well, on a graphic EQ, remember that slider takes a third octave with it. So you're going to take a third octave worth of frequencies in order to kill a sine wave. Does it work? Yeah, it works, right? That frequency doesn't feed back anymore, but you took a whole bunch of other frequencies with it that nobody ever gets to hear again, okay? So I think that, you know, that strategy is, I'm not going to say it's wrong.
But it has its downsides.
It comes with some really significant consequences, right?
Yeah.
Negative consequences to the quality of your system. So I would consider that the absolute last resort. And that's a very widely misunderstood concept, even among sound professionals. They don't understand, a lot of people don't understand that this is really a geometry problem rather than, you know, a frequency problem. Because it's so easy to just reach over and notch out a frequency on an EQ. But, you know, then you're killing all those frequencies.
Yeah,
now,
right.
If you're doing, you know, sort of an industrial show or a commercial show or something where you're coming in one day and you got to make this thing happen, you're coming in at 8 in the morning and the show happens that night and then you're out at the end of the night, you know, you may not have a whole lot of time to move your loudspeakers and mics around, and maybe the people have really poor mic technique, and maybe leveraging this geometry solution just is not in the cards for you that day, and you just need to get through the day. No one cares whether the frequency response is awesome or not. They just want it to be louder. In that case, yeah, the EQ might be the way that you get through the day without people shouting at you. And you just have to accept the consequences of that it's not going to sound very good, but at least it'll be loud and it won't be feeding back. But I would strongly advise you to not use that as your first line of defense. You can get much better results by especially just moving that mic closer to that talker. Other strategies, for example, could be never let the sound of the mic go through a loudspeaker that is pointing at the mic. So if you've got a, like a monitor loudspeaker that's coming up from overhead on stage or maybe from the sides, you should probably not put the voices through that because those voices are going to hit the mic and you'll get feedback. So it's actually pretty common, particularly in musical theater where you're using these omnidirectional microphones, it's pretty common to just not do vocal foldback, vocal monitoring. And the actors are going to ask for it all the time. Of course they will, because that would be really helpful to them to be able to hear themselves and the other people around them. I understand how that would really make their life a lot easier. But doing that often means that you don't get to let the audience hear them because you just lose your feedback, your gain before feedback. So I usually push pretty hard when I'm doing musicals on vocal feedback or vocal foldback. I usually just say, no, I'm sorry, you just can't. I wish I could give you your own voice in the monitor. I really wish I could. But if I do, then I can't give your voice to the audience. And the only time I've ever been able to do vocal monitoring like that is if I've got a boom mic, that's coming right here in front of their mouth, especially if that's a directional boom mic. Then you can usually get away with the vocal foldback without too much trouble. So it could be that was the other problem, is maybe you guys had vocal foldback on stage and you needed to.
Yeah, a lot of what he was doing was on the near fields and stuff that were causing a lot of problems.
Yeah, so, again, you're going to obliterate the frequency response in order to.
Yeah, on your near fields that you're being all fiddly with anyway.
Yeah, and maybe that's okay, right? Because the actors just want to hear themselves. Maybe they're not going to complain too much if it sounds crappy, as long as they can get the general gist of what's going on. As long as you're not having to do that for the loudspeakers pointed at the audience. So still not a practice I would recommend, but it's definitely one you're going to see out there. Other questions? All right, so let's take a look at acoustics. So acoustics is the study of what happens when sound bumps into something. Okay, that's basically it. What happens when sound runs into something? And there are people that will devote their entire professional lives to answering that question. So there are really 4 possibilities of what could happen when sound bumps into something. That sound could hit an object, and we already know that in certain circumstances, the sound could go around that object, right? We learned that like the first week of the semester, that if the object it's hitting is small relative to the wavelength of that sound, then that sound's going to go around that object. So that's option 1. We know about that. But if the object is large, then one of these other 3 things could happen. That sound could be reflected off of that object. What is happening here, you've got this sound wave, it's pushing on those air molecules, and eventually it finds something, solid or hard, pushing against it, and that energy can't go through that thing. So where's that energy going to go? It's going to build up and build up and build up. And sound is, air is elastic, so eventually that energy is going to explode back the other direction off the wall. That's called an acoustic reflection. So some of that energy could be reflected off the surface. There's another option, which is that depending on what that surface is made out of, some of that energy could get kind of sucked into that object. And that would be called absorption. So maybe some of that energy is pushing up against that object, and some of it's able to get through it. So it gets absorbed. And then the 4th option is transmission. And transmission is transmission can be 2 different things. It could be the sound getting through the object, and you get to the other side, and there's still some sound that you can hear it, right? You can hear it getting through the walls. That probably happens at your apartment, where the noise from your neighbors gets through the walls. You have some transmission through the walls. The other option is the surface or the object that the sound is hitting could retransmit that sound by vibrating sympathetically. So if that surface is of a certain size and a certain thickness and a certain property that allows it to shake or vibrate in a similar way that that sound wave is oscillating, then that new object becomes a new sound source and it retransmits. It's like a radio repeater. Okay, it starts shaking. This is what happens with a lot of musical instruments, like a guitar, for example. You pluck a string from the guitar, and that vibration of the string starts to vibrate the wood membrane on top of that guitar, and that guitar retransmits through the wood the sound out louder. Okay, So that's another option that could happen. So what does that mean? And how does that become part of our world? Well, before we can really understand what happens here, we have to have some way of measuring these different behaviors. So there was a lot of research for a lot of years of folks who were trying to figure out a way of measuring this stuff. And one was called the Sabin. And there was this guy named Sabin, and like every sound person that ever invented an idea, named it after themselves so they could live forever. And Sabin was no exception. So Sabin was sort of one of the really early acousticians, right, that was trying to figure out a way of talking and measuring these things. And what he was trying to figure out was a way to measure absorption and reflection, right? How can you measure that or weigh it and put a number on it? And he said, and he basically zeroed in on this notion of like, well, you know, in sound, everything we do is a comparison, right? dB is all about comparing one level against another level. So what would be the comparison? What's the reference level for reflection and absorption? For example, we know the reference level for sound pressure level is 20 micropascals. That's the quietest sound we could hear. So we measure everything off of that. So he's thinking, well, what is the reference point for reflection and absorption? He said, well, there is probably out there some hypothetical perfect reflector that reflects 100% of the energy, but I don't know what that is. He said, but I do know a surface that would absorb 100% of the energy, the sound energy that hits it, and that would be an open window. So if there's a window on this wall and that window was open, then all of 100% of the sound energy that hits that surface area where the window is, 100% of the energy would be absorbed. It would disappear into that hole and not come back. Okay, so he decided that that was his perfect absorber, an open window.
But wouldn't it not be absorbed? It would just go through the window and eventually hit other things.
Well, sure, but after it's left the room, I don't care about it anymore. So he's just thinking about what's going on inside of my room. And once it goes through that window, that is the same behavior as it being perfectly absorbed.
It's like throwing hot oil out your window and being like, it's gone.
It's gone, right? It's like throwing out the trash. It's gone.
It doesn't exist anymore.
Yeah, it's not piling up somewhere. You know, it's gone. So that was his basic thought is, okay, once it leaves the room, then I don't care about it anymore. So that's my perfect absorber. And then, so if an open window is my perfect absorber, then my perfect reflector is some sort of unobtainium that is the equivalent of no open windows, right? 0% of open windows. So this is probably sounding a little weird to you right now, and it is. It's kind of a crazy way of thinking about things, but it kind of made a certain amount of sense, and it allowed for some conversations and some math to happen. And so Sabin created his own unit of measurement called the Sabin. So 1 Sabin is equal to 1 square foot of open window. So for every square foot of open window you have, you get a Sabin. So if you have 10 square feet of open window, you have 10 Sabins. What do you do with that information? Well, let's try this out. So let's say you have some material. I'm going to try to use my annotation thing again here. Hopefully it'll work. Actually, I bet I could do it this thing. Should try it. Okay. Let me move my keyboard here. All right. So let's say there is a certain material in this room that has what we would call an absorption coefficient of 0.1. Okay. Oh, we've got an arrow on that. That's cool. So 0.1 is it absorbs 10% of the energy that hits it. Okay. And let's say I have 100 square feet. Oh man, I'm getting all kinds of cool things here. Okay, but that's not working. Let's try something else here. Getting thought bubbles and.
Is there not a text feature?
Yeah, that's probably better. So let me try that. Oh, yes, there it is. Delete, delete, delete. There we go. Yes, let's try this. Okay, so I have some sort of material that has an absorption coefficient of 0.1. Absorption coefficient. And remember, like I said, that means that it absorbs 10% of the energy that hits it, and the rest of it gets reflected. Okay. Now let's say I have 100 square feet of that material. Then that is equivalent to 10 Sabines.
And a Sabin is an open window?
1 square foot of open window.
Okay, cool.
Okay. So I've got this, that whatever this material is, let's say it's, a brick wall. Okay. Absorbs 10% of the energy, reflects 90% of the energy. I have 100 square feet of that stuff, and therefore 100 square feet of brick has an absorption level that is equal to 10 Sabines, or 10 square feet of open window. So there you go. That gives you some idea of how much sound will, come back at you in that room.
Why is it measured through open window or square footage and not by just percentage of like how much sound? That feels like a much more helpful amount to know.
Such an excellent observation. You have zeroed in very quickly on the problem with Sabines.
Okay, great.
So the problem with Sabines is Sabin created a unit of measurement that is dependent upon another unit of measurement.
Feet.
Which is feet, right? Well, setting aside for now the sort of metric issue, which would really mess this up, then, having a unit of measurement that is defined based on a separate unit of measurement there's kind of an efficiency problem there. So the way we tend to talk about it right now, I mean, the concept of the Sabin has kind of fallen out of fashion. Instead, we like to talk about average absorption coefficients, because that's basically what Sabin was trying to do, is he was trying to sort of like add up the absorptive properties of all the surfaces in the room and then define that room based on the number of Sabines that room represented, the percentage of perfect absorption. And knowing that the percentage of perfect absorption in the room would give you some sense of how much energy would be reflected and how much energy would be absorbed. Now, but it has these problems. So instead, nowadays, we tend to think about average absorption coefficients. So let's see if we can demonstrate how that works. Okay, so let's say I have a room that has 1,000, and we'll do this in meters just to show how you can avoid that problem with the Sabines. So let's say this is 1,000 square meters of total surface area. So if you add up all the walls, the floor, and the ceiling, all that surface area, you get 1,000 square meters of total surface area. Now let's say 200 square meters of that surface area has an absorption coefficient of 0.8. Two Fs. And the remaining 800 square meters has an absorption coefficient of 0.1. Okay, so this is the scenario. So in that situation, we could say that the 200 square meters of that is a 0.8 absorption coefficient, we could just do 200 times 0.8, and that would get us what? Anybody do that math?
80? Wait, no, one. Damn it, I tried to do it in my head. It didn't work well.
Should be 200 times,
160.
yeah, 160. So 160 square meters of perfect absorption. Now, some people will still call that Sabins, even though strictly speaking, it's not. But it's 160 square meters of perfect absorption. Okay, and then the other one would be 800 square meters of stuff times 0.1. What does that get us?
$80.
Yes. So now we got
Oh, 800.
80.
I did 200.
Oh, so 80 square meters of perfect absorption. Okay.
Muted.
So if we add that up, we do 160 plus 80, and we get
240.
240 square meters of perfect absorption. We could call that 200 Sabins if we wanted to. It doesn't really matter. But here's where the rubber meets the road. So if we've got 240 square meters of perfect absorption in a room that is 1,000 square meters of total surface area, we could say 240 divided by 1,000, and we get what? 0.24. That is the average absorption coefficient of our room.
So the majority of the room absorbs 24% of.
Well,
sound.
just the room in general.
Oh.
You put sound into that room, and 24% of that
24%.
sound will get absorbed when it hits the walls, and the rest comes back at you.
Why are we looking at all, like, the room as a whole rather than kind of individual? If we're looking at directivity, you know, like parts of the room are going to absorb differently.
Well, you know, so we're in this scenario, we're really looking at, you know, just generally sort of how much sound comes back. This allows you to think about things like reverberation time, think about, you know, the general noise floor that would happen in the room, because that's what we're going to talk about here now, is that what happens when sound actually starts floating around inside of a room. And being able to think about the room as a whole can kind of help you with that. So this notion of average absorption coefficient allows you to calculate this independent of any particular unit of measurement. It's not tied to feet or meters or anything else. And it allows you to calculate dB loss. So for example, if your average absorption coefficient, let's just say it's 0.2. That means 20% of the sound would be absorbed, 80% would be reflected. So we could do a little bit of math here, and we could say that, now we would do a 10 times the log as opposed to a 20 because of
Power.
comb filtering.
I was going to say reasons.
Okay. So what I would do is 0.8. So if 20% gets absorbed, then 80% gets reflected. So I'm going to say 0.8 log 10 times 10. So that means we have a minus 1 dB based on the absorption. So the sound that comes back at us off the walls is going to come off the walls on average in this room a dB quieter than it was when it hit the wall, which is not a whole lot. All right, so let's take a look here at some stuff. So here's an example of some absorption coefficients. And you may have guessed this already, but it's dependent on frequency. So here's different materials and their absorption coefficients per frequency. Take a look at that for a second and tell me if there's anything that makes you, you know, think, that's interesting.
Everything above 1 makes me think, that's interesting.
That is interesting. Yes.
0.12.
We'll talk about that.
I was going to say.
So we'll talk about that in a second. What else? Okay, look at these ones here, the two acoustical tile ones. So this is the same material. What's different about it in these two situations?
Suspended or mounted on concrete.
Yeah, so in one case it's glued to the concrete ceiling, and in the other case it's suspended, meaning there's a, you know, it's below, there's a certain air gap below that ceiling. And what changes? Well, that air gap changes the absorption coefficient pretty dramatically. you know, at 2 kilohertz, you go from being like 50% absorption to almost a full 100% absorption just by creating an air gap. The reason here is because that sound will hit that tile and absorb some of that energy, but some of it gets through, right? And then it travels up, hits the concrete, comes back, and in that round trip, it's gotten quieter, right? Because of inverse square law. And then it goes through the tile again and gets absorbed a second time. So you get a lot more bang for your buck if you can give yourself an air gap between things. This is true of curtains or anything that you would put on a wall to try to absorb sound. If you can put some air between the wall and the thing that's absorbing, it's always going to absorb better. So the other thing you might notice is that it's much easier to absorb high frequencies than low frequencies, isn't it? Right? The high frequencies have much higher absorption coefficients than the low frequencies. Why? Because of surface area. Okay, if you want to absorb a really low frequency, you have to have that absorptive material has to be as large as the wavelength of that particular frequency.
So what does work well for low frequencies then?
Really, really big panels or really, really thick panels. So like if we were back in our lab right now, I could show you in the corners, you might have remembered that we have those acoustic panels and we corner load them. And there's a gap behind there. And those are bass traps, okay? The idea there is to give a little bit more space for those low frequencies to get absorbed. We're effectively making that thing thicker. Grayson, you had a question or a comment?
Yeah, 2 questions. First question, so why is it that at 250 hertz, it's like there's a spike in how much acoustical in the absorption coefficient?
Yeah, I don't know.
Fair enough.
It could have something to do with the distance between the wall and the tile. That just happens to be a distance that is sympathetic to that particular wavelength.
Yeah. So my second question is, like, I know that having whatever is absorbing it, the size that that's going to be is going to be depending on what frequencies come in and out and whatnot. What about the air gap? Is there like a certain like kind of set standard size that you like?
Yeah, not really. Yeah, not really. But generally, the bigger the gap, the better, kind of, because you can leverage inverse square law as much as possible. Because that sound gets quieter the farther it has to travel before it comes back through the tile.
So how did you know to do that for the bass traps in the lab?
Oh, they're designed that way. So we got 2 different types. We got types that flush mount to the wall and others that are beveled on the back to allow you to corner load them to create bass traps. They're designed to do that.
Okay.
I didn't invent that. That was just, you know.
Yeah, I was just wondering if you had like had an idea of like how far up away from the wall you needed it to be.
Yeah, no, it's designed that way. It's based on the bevels that are on the back of the tile. Okay, so yeah, let's talk about this one that Lance has, where he noticed that in that Wenger absorption tile, it's claiming an absorption coefficient of 1.23 at 500 hertz. Now let's just wrap our heads around what that means. They're claiming that this thing can absorb 123% of the energy that hits it.
Yeah, hell yeah.
Yeah, that doesn't seem, that can't possibly be.
No, I totally buy it. It's stealing energy from the air.
Right.
Absorbs light too.
All right. So here is, yes, I've highlighted it. So here is the kind of tile we're talking about here. So look at that picture there. So these are the kind of tiles we are. See if you can look at that, figure out, put yourself in the mind of the marketing person who is going to try to make this thing look as good as we possibly can without technically lying. So how could I not lie, but come up with a scenario where this tile absorbs more than all of the energy that hits it? Keeping in mind the way that we calculated the absorption coefficient a few minutes ago, because they're doing that same math. They're doing it on this tile.
Would it absorb sound from the outside of the room as well?
No.
Okay, I don't know then.
Does it absorb more sound than you can put in the room?
No. So, let's first just say that obviously it's not doing 123% absorption. So it's not actually doing that, but they're also not technically lying.
So you're saying that it is, but it isn't.
Right, exactly. That is exactly what I'm saying. It is, but it isn't.
It depends.
In theory, it is 123% absorption, but in actual practice, due to certain reflections based off the parts of the wall that aren't being covered, gain and
Yeah, no, not really.
that thing.
So think
Okay,
about.
wait, I have an idea.
Okay.
So if it's by square feet, which is stupid,
Yeah.
it would be, right, like you have the area that you're trying to measure.
Yeah.
If you have the absorption area that is larger than absorbed,
Yeah. Why is it
area?
larger? Why is it
because
larger?
you put more panels in the room.
Oh, you're so close.
Oh,
So it's no, but you're so very close. You're almost there.
Is it because the panel is bigger than one square foot? Like the distance of it is some very,
No.
I don't know.
No. Okay.
Wait, hold on. Last one. This is even stupider than all the. Is are you trying to say that there is more like theoretical square feet in there than there is actual square feet in real space?
Yes.
Yeah. Because it like makes it travel farther to.
No.
No.
Okay. So look at that tile.
Yeah.
It covers a certain amount of square footage on that wall, right? But the total square footage of surface area of that tile is larger than the square footage that it covers. Why?
Oh, because sound square footage, because we're assuming that it's an open window.
No.
Because that opens a portal, right?
Has the potential to cover this space, but it's never going to cover that space because it's not actually that big. It's like when you look at a dog that has like really big. Well, that's going to be.
No,
You're
it's way simpler than that.
Because
Is it just because there's a side to the tile as it's
Yes. So the tile is thick, right? So that thickness, that 4-inch thickness around it introduces new surface area that is absorptive into the room, right? And so you get to count that surface area against the surface area that got covered up. So you are actually covering that spot on the wall with an amount of absorptive surface area that is 123% of the area that got covered.
Oh, because when you're including the sides, you're covering wall space that doesn't exist.
Yes. Okay.
So what if you put like a sphere? What would a
Well, then it would be,
like,
yeah, then it gets really complicated. But remember, this is the marketing person trying to make this look really great. So they're not technically lying because, yes, okay, that makes sense. That is true. But in practice, yeah, it's not absorbing 123. I mean, that extra 0.23 is nothing, actually. It doesn't really do that in a way that you could measure, right? Because it's really just all about when you're going to buy this stuff, you're trying to figure out how much do I have to buy to cover up the right amount of surface area. So the fact of the thickness is really more, the thickness impacts the extent to which it can absorb lower frequencies more than it affects the total absorption in the room. So every acoustician that I have ever known or ever spoken with, they just ignore that extra absorption. That is the theoretical. They just call it 100%. They call it an absorption coefficient of 1, even if the manufacturer says 1.23 or 1.3 or whatever. So let's just keep that in mind, that they're trying to make this look better than it really is. Okay. All right. It is 11:20, and I still have, I think, 3 more slides. So given that I'm trying to make up some lost time here, I'm going to go ahead and do those 3 more slides. If you need to go off because you got another class or something, feel free to. I'm going to keep recording, and you can ask questions after that. But I'm going to keep going if that's all right. Okay.
Yeah.
So All right, so let's talk about what this means now. So when sound reflects in the room, you hear it, right? It goes out to the wall and it comes back at you and you get to hear it again. And that manifests itself in a couple of different ways. One is in what's called reverberation. So reverberation is what you hear when the sound gets reflected. So let's say you put something in a room, it's an omnidirectional sound, and it radiates sound every direction. And so that sound that's coming from that thing, it's hurtling through the air at 1,000 feet per second until it runs into a wall. And then when it hits that wall, a certain amount of energy gets absorbed, but the rest of it gets reflected and bounces off the wall, travels across the room at 1,000 feet per second again, until it hits another surface. Same thing happens. A little bit gets absorbed, some of it comes back. So it's going back and forth all the way around the room, and it keeps doing that until eventually all the sound goes away, either through absorption at the wall or just loss of energy for inverse square law. Okay? Well, while that's happening, remember that's happening in every direction at every surface. So you end up, it's a big mess that gets created of all these sounds that are bouncing around back and forth and back and forth. And eventually, the different sounds start getting so close together in time that it sounds like one continuous sound. And that is reverberation. Reverberation is that long decay of sound that it doesn't sound like an echo. It just sounds like, you know, a tail of sound that it slowly gets quieter and quieter and quieter. We measure that in what's called reverberation time. So as that sound source is radiating into the room, you keep pumping energy into the room, and that energy keeps getting absorbed and reflected and absorbed and reflected, and eventually you're going to achieve an equilibrium where the sound is getting absorbed or it's disappearing at the same rate that it is being put into the room. So it equals out. So you no longer hear anything getting louder, and you no longer hear it getting quieter because you're pumping it in at the same rate that it's being reflected and absorbed. When you get to that point, that's what's being shown in this graph. It goes up, and eventually it levels out. And then if you cut off the sound source, the loudspeaker or whatever, then you're no longer pumping energy in the room, and all that's left is the energy that's bouncing around. And that will slowly decay. Eventually it'll go away. The amount of time that it takes to do that is called the reverberation time. And we call it RT60, RT standing for reverberation time, 60 meaning 60 decibels. So we tend to measure it based on how long it took for that sound to decay 60 decibels, because after 60 decibels, we usually don't hear it anymore unless it's a really, really quiet room. So generally speaking, measuring reverberation time is more effective when you use a longer sound rather than like a hand clap. Like a hand clap can give you a sense of general reflectivity, but if you really want to measure reverberation time, you need to generate some sound for a little while. And sometimes that's just a few seconds. And we did that in intensive arts when we were doing those long swept sine waves in that auditorium at the high school, and we were able to get reverberation time based on that. So here's what happens. Here, you also have this, this thing called the direct and reverberant sound field. So here is your listener, and the listener is hearing the sound that is coming directly from the talker straight to their ears. It hasn't bumped into anything, no reflections, no anything, just direct sound straight from the talker to the listener. But the listener is also hearing the sound be reflected off of different surfaces. And there are some reflections that we would call early reflections. And the early reflections are the reflected sound that is really only bounced off one, maybe two surfaces before it gets to the listener. So you can see like the shortest reflection is this one that goes from the talker, bounces off this little ceiling area here, and hits the listener. Then the second one is the sound that goes off the back wall behind the talker and then bounces off and gets to the listener. And then the third one is this one that goes up to this part of the ceiling and hits there. Fourth one is the one that hits the back wall behind the listener and then comes back. And then the fifth one actually now you're bouncing off two surfaces. Now, one that's not included in this slide is the floor. So if there really was only one listener and there was nobody sitting here, then you would also have a floor bounce reflection that would get to the listener. These are called early reflections. So early reflections tend to be the reflected sound that arrives at the listener within the first 30 milliseconds or so after the direct sound. And usually those reflections have only bounced off one surface. These early reflections, you can sometimes kind of hear the difference between them, like you hear them as distinct echoes. Now, it is the early reflections that give us a sense of the size of the room. So a larger room is going to have early reflections that are spaced farther apart and are a longer amount of time between the direct sound and the early reflections. And then eventually you start getting the sound that's bouncing off lots of surfaces, and that becomes the reverberation. So the actual direct to reverberant sound field is a mix of the direct sound, which we sometimes call the dry sound, the early reflections, and the reverberation. And it's a mix of all three of those things, and that's what we hear in any room. Here's where this can become a problem for you. So if we just lump the early reflections and the reverberant field in together, then we could have we could graph it like this, where the hollow dots would be reverberant sound and the solid dots would be direct sound. So there's this thing called critical distance. And critical distance is the distance away from the loudspeaker or the talker or the whatever that's making the sound, the distance you get away from that before the reverberant sound is the same level as the direct sound. So how far away from this loudspeaker do I go before I have the same number of solid dots as I have hollow dots? So I'm going to say it is right about here. Okay, this area. I'll see if I can draw a little. Can I? I don't know. Oh, I'll do that. I'm going to say somewhere around, oops, here it is. It's right around there. Yeah? That's around the area where the number of solid dots and the number of hollow dots are the same. That's my critical distance. So what's important about a critical distance is, in this case, the reverberation is basically noise. And in order for intelligibility to happen, in order for us to be able to understand the information that is coming from the talker to the loudspeaker, the direct sound needs to be, the peak levels, the peaks of the direct sound need to be around 20 dB or so, 20 to 25 dB louder than the noise floor. Or in this case, 20 to 25 dB louder than the reverberation. And if it's any less than that, you're going to have a hard time understanding. So once you get to that point where they are the same level, you really, after that, these people that are behind that red line, they're not going to understand anything. It's just going to sound like a big, echoey, reverberant mess. So if you still have audience standing and sitting out here, they're not going to have a very good time at this show. Okay? So let's talk about some ways we can improve that critical distance. So here I've got the same scenario up on the top, but what if I went to a more directional loudspeaker? Right? I put a horn on this driver. Now I'm controlling where that direct sound goes. Less of it is hitting the walls. If less of it is hitting the walls, then less of it is bouncing off the walls. And therefore, I get less reflected sound. So now my critical distance is now somewhere over here. Right? It's right around here that I'm getting equal number of solid dots to hollow dots. So I've made it almost all the way to the back of the room just by keeping the sound off the walls. So here's another variable for you when you're designing your sound system. Yeah, you want to disperse the sound evenly across the audience area. And yeah, you want to keep it off the stage, but you also want to keep it off the walls as much as you possibly can. Let's look. Can anybody think of another way that we could improve the critical distance here besides using a directional?
Acoustic panels?
Yeah, so if we could somehow make these walls less reflective, put some absorption on there, then we would have less hollow dots coming off the wall. That could improve the critical distance. What else?
Is saying more than one loudspeaker allowed?
Ah, yeah. So what if we could put another one sort of here-ish, right? And it would introduce another now mess of solid dots. And now my critical distance is much farther. Yeah. Here's a way that you will not improve the critical distance. So here you've got these people all the way in the back, and they can't understand anything that's going on. And what are the words that they're going to use to describe their experience?
It's too quiet. Can't hear it.
Yeah, they're going to say, we can't hear back here. Now, that's not strictly true. They can hear a lot of things. They just can't understand what they're hearing. And so a lot of times people say, I can't hear it, I can't hear it. And what are you going to do? You're going to turn it up, right? You're going to push the fader up. Well, what happens to our critical distance when this loudspeaker gets louder?
Not a lot, right?
Nothing
It
will happen
stays
to our
the
critical
same,
distance,
yeah.
right? We still have the same ratio of solid dots to hollow dots because that louder sound will just reflect off the walls in the same way. So turning it up is not going to solve that problem. You've got to solve that problem some other way. And I've been in situations like this before where we have intelligibility issues and people are saying, I can't hear it, turn it up, turn it up. And the problem doesn't get solved because it's a critical distance issue. You've got to either add some more loudspeakers further down the room, absorb some at the walls, get more directional with your loudspeakers, or maybe all three of those things would get you a better result.
If you
Okay.
turned it down, would you have a better chance at increasing intelligibility?
No, because that ratio would stay the same, right? The ratio of reflected sound to reverberant direct sound would still be the same. You'd still have no intelligibility, even if it got quieter. But this is part of the reason why, if you've ever even seen people talking when they do this and cup around and try to haul, what they're doing is they're directing the energy away from the walls and more in the direction they're talking, and the intelligibility goes up, right? They're increasing the critical distance simply by doing this. You could do the same thing with your loudspeakers. But this is also a big reason why we do delay fills. I've seen some sound systems in old cathedrals that are really reflective and reverberant. And of course, they don't want to put absorption on the walls because that would destroy what the room is looking like and trying to do. So instead, what they'll do is they'll put little speakers on the back of the pews in the cathedral, so that each person is never more than 2 or 3 feet away from a loudspeaker, and therefore the critical distance is really good, despite the room still being really reverberant. Those are some kind of rules of thumb for acoustics, reverberation, absorption, reflection. Let me just review really quickly what I'm going to ask you to do for the assignment. If you may have looked at it already. So let's see. I'm going to have you, if you are, yeah. So here is the little worksheet here. And if you download that PDF, here's what it looks like. So I'm going to have you calculate some acoustical gain for the Stevens Center. All right. And I've also given you the CAD file for the Stevens Center, and it's marked up in a way that tells you where things are. So let me pull that up and let you see what that looks like. Oh, goodness. All right, I'm going to deal with that later. Okay, let me try this again now. Coming. Okay. So I'm saying this is where the center cluster is. All right. And what I'm asking you to do is to, let's see. Here it is. So I'm asking you to, in the Stevens Center, assuming the center cluster and the microphone are omnidirectional and that center cluster location, you're going to calculate answer for the talker standing at the plaster line with a microphone 6 inches from their mouth and the listener sitting in the back row. Okay, so you should be able to go to this CAD file, put a talker standing here at the plaster line and a listener over here at the back row orchestra, and figure out what that acoustical gain will be. And then I'm going to have you think about what directivity would do for that. So a directional loudspeaker, directional microphone. So that is the basic homework. And Lance, I do have somewhere in here. I don't think I thought I had posted it, but now I don't see it here. I've got one that's a little bit harder for you. You're going to do that, and then I'm also going to have you calculate some absorption coefficients. Okay, so I'll post that here after the class. I know I created it. I just haven't put it up on the Canvas yet. So I'm going to have you do that. Now let's take a look and see when that is due. It is due on Friday. Okay, so I want you to spend the week working on that. And then what we'll do is we'll go through it. And I don't want you to turn it in until after class is over, because it's the same thing we did with the other ones, where I'm going to have you, well, you know, I'm going to take you through it. We're going to figure out what the answer is. You fix it, and then you turn it in. Okay? Any questions about that? No, that makes sense to everybody?
All good, dude.
Sounds good to me.
Okay, so that is your job for the week, is work through that little worksheet. Shouldn't take you too long, and then we'll go over it on Friday. And again, use the discussion board if you want to have conversations or help each other out. And I will try to have my Zoom on Monday, Wednesday, Friday from 3 to 4 if you want to get some real-time help through that. Okay, any other questions before we stop?
No, I'm good.
All righty.
All
So
good.
I will see you all on Friday then. And let me know if you run into any trouble in the meantime.
Take care.
Thank you.
Thank you.
Happy quarantine, Jason.
Thanks. All right, talk to you later. Bye.